Hi everyone. So previously we had discussed on the bell numbers and the Catalan numbers algorithm. Yeah, mainly that uses DP. Right. So now we'll be going with a tree DP algorithm, mainly nothing but also called as dynamic programming on the trees. Right. So let's get into the definition part here. So what does it state here? Tree DP or the dynamic programming on the trees, it is a technique that calculates or computes the answers for the tree problems. Yeah. How? By combining solutions of children to form the parents' solution. By combining the solutions of children, we will be combining the solutions of children here within the algo to form the parents' solution. To form the parents' solution. So it commonly uses DFS. So we'll be making use of the post order DFS, right, within the algorithm to compute the state values. To compute the state values, so we'll be making use of the post order DFS, right? So you have to know the post order traversal, right? So we'll be making use of the DFS post order, this one. DFS post order to compute the state values. Suppose, for example, it may be include or excluding a node for the each node, right? So this avoids recomputation as we are making use of the DP and exploits the tree structure, right? So this is the simple definition part. Now let's move on with the explanation part. So a common pattern in the tree DP or the dynamic programming on trees is to maintain the multiple DP states per node. So this is very important. Just listen to this carefully. Just remember this. Also remember this. This is one of the important points. A common pattern in the tree DP is to maintain the multiple DP states per node, right? If you would have solved the DP on trees problems, we have solved n number of this one, what do we call DP on trees problem, right? So while we solved the DP problems, certain DP problems, we went with a DP on this one, DP on trees, where we went with a centroid and other stuff to solve the problem. That is fine. But basically, we have solved the DP on trees problem. If you remember the Codeforces problem, some of the problems we solved while solving the DP based problems. Yeah. Now, a common pattern in the tree DP is to maintain the multiple DP states per node that represents different constraints that represent different constraint. For example, whether the node is chosen or not, whether the node is chosen or not, right? So here what we will be doing, we process the tree in post order, right? So we process the tree in post order, nothing but child first or the children first. We will be processing the tree in the post order. First comes the child or the children, then we will be computing the DP states for every child, right? And then we will combine them to compute the parent states. After computing the DP states for every child, then we will combine them to compute the parent states. So this is why we will be making use of the post order basically, right? So this is especially useful. So see use cases. So this is especially useful for the problems like this one, maximum weight independent set on a tree. This one, maximum weight independent set on a tree, tree vertex cover, subtree sums, or the longest path computations. So especially used in the longest path computations as well as the subtree sums. Usually, as far as I know, as far as I have solved, right, as far as I have given the this one contest, basically most of the problems will be based on longest path computations and the this one, what do we call, uh, this one subtree sums actually usually will be going with the uh, tree DP, right? So we'll be making use of the tree DP. Usually we will be making use of the DFS post order DFS to compute the this one, what do we call, DP states for every child, and then we will combine them to compute the parent state. That's what we'll be doing. So that one sentence you have to remember at any cost, right? So this is fine, man. Now let's try to implement the same thing in the form of algo, right? So here first we'll be making use of the Python programming language. So let me go with import sys here. This is fine. Next, let me go with sys dot. Let's set the recursion limit, right? So we'll be making use of the recursion here. Let's go with the set recursion limit here. Let me make use of 10 to the power of 6. Let me make use of exponentiation operator here. 10 to the power of 6. Fine. Now, what we will be doing here, just remember this, whatever I say, each node has a value, weight, right? So value, we call it as weight. We have solved Floyd Marshall, we have solved Digistras, we have solved this one, Johnson's, everything, most of the things, right? Now, you have to know what is weight. So along with the edge, we will be giving with the, we are given node edge, along with the edge, we'll be given the weight as well. weight, it can be for the particular edge or it can be for the particular node, right? So each node has a value or the weight. Actually, it is considered as weight. Tree edges define tree edges. The edges of the tree define parent-child relationships. Parent-child relationships. That this is fine. We must select the nodes such that no two adjacent nodes are both chosen, right? So we must select the nodes such that no two adjacent nodes are both chosen here, maximizing the total weight. Maximizing the total weight. Suppose let's consider the very simple example for this particular this one algorithm. So let me consider here example. Suppose this is node 0. Let me write this one directly. Suppose this is node 1. Suppose this is node 2. From 2, suppose we are going to this one. The children are 3 and 4 respectively. And from this one node 2, let's consider 5 and 6 respectively. Yeah. So wait, let me consider this one 3 actually. For the 1, let me consider the weight 2. For the 2, let me consider the weight 1. So for the 3, 4, let's consider 1 and 5, something like that, right? So for the 3 and 4, let's consider 1 and 5. And for the 5 and 6, let's consider the weight 4 as well as the 6 respectively. 4 as well as 6 respectively, right? So we are going with 3 to 1, 1, 5, 4, 6. 3 to 1, 1, 5, 4, 6. Yeah. So this, let's consider the same example, right? So 3, or we are going with the DFS, right? So let's go with the depth here. 311 here. 3211. Sorry, 32. This one value actually we are considering, right? So 3. This one weight 3 2 double 1 here, right? So double 1 this one 3 2 double 1, then followed by 5 4 6, right? So this one 5 4 as well as the 6. Yep. So let me delete this one entirely. Let's consider the same example. So I'll just go with values equals 3 2 1 1 here 5 4 6. Yep. Now after considering the values, let me assign this one to the length. We'll be making use of this one everywhere. So let me assign this one to the value n. So I'll just go with n of values we have considered, right? So this is fine. Now let's build the adjacency. This one list actually. I'll just go with ADJ here. This is fine. Yep. Now for underscore in range, in the range n actually, in the range n, then let me assign the edges to 0 comma 1. So let me delete this one. 0 comma 1. So this is fine. uh 0 comma 2, so this is also fine. Let me go with 1 comma 3. This is fine. Next, let me go with 1 comma 4. This is also fine. Next, let me go with 2 comma 5. So we are going with the adjacency list for the graph that I, for the tree that I had drawn, right? So same thing, you can just check. So this one will be 2 comma 6. Yeah. So you can just go to the video where I had drawn this one to the tree actually. So there you can consider the edges. So we are just going with the adjacency list here. So let me go with for u comma v as we are considering the adjacency list here and edges, right? Edges variable name. So let's do one thing. Let's go with the adjacency of u. Mm, So let's append v to u. So this one is fine. Let's do the same thing vice versa, right? So this is fine. Let me go with here u and this one has to be v. Yeah. So let me come out of this one entirely. Now let's go with the DP arrays, right? So I'll just go with DP include and DP exclude. DP include is nothing but the best sum when node is included, and DP exclude is nothing but the best sum when node is excluded, right? So I'll just go with DP include here. So let me initialize this one to 0 to n. Yeah, this is fine. The same thing, let me go with the DP exclude here. So this one will be same thing, 0 into n as well. Sorry, n as well. Yeah, now we have successfully this one initialize the DPRS. Now we have to perform the post order DFS, right? So let's go with the DFS function, helper function. So this one will be DFS of, let me go with u, comma parent. So this is fine. So the first thing here is we will be going with a post order DFS just to calculate or compute the DP values. So let me consider include sum and initialize this one to the values of right. So if u is included, suppose we are considering if u is included. So what if u is excluded? So I'll just go with the exclude sum here. We initialize to the value 0. This is fine, man. Now let's do one thing. We have to explore all the children, right? So we have to explore all the children that is present in the tree. So I'll just go with for v and adjacency of this one of u actually. If if it is equivalent to parent, if it is equivalent to the parent, then we have to give continue. Then we have to give continue. Next, what shall we do? Let me go with the DFS of v comma u. Let me go with the DFS of v comma u. Right? So this is fine, man. Now let's go with the include sum and exclude sum. Include sum equals include sum plus dp exclude of yeah, this is fine. Children must be excluded here. This is fine. Now let me go with the exclude sum. This one exclude sum equals exclude sum plus max of dp. This one basically dp include, I believe. Yeah, dp include of v, dp include of v along with the dp exclude. Let me go with the dp exclude here of v as well. Right, so this is fine. We have to choose the best for each child. So this is fine. Now let's do one thing. I'll just go with dp include of u, dp include of u. Let me assign this one to the include sum as well as same goes with the dp exclude of this one u itself. Let me assign this one to the exclude sum. This is fine. Yeah. Now we have to run the DFS from the root 2, nothing but the node 0 that I had already shown the graph actually, tree actually, sorry. So let me run the DFS from 0. Yeah, node 0. Yep, this is fine, I believe. Now we have to compute or calculate the final result, right? For that one, let me consider the variable answer here. So this one will be max of dp include of 0, dp include of 0 and dp exclude of 0 as well, right? So this is fine. Then let's print the results, right, for the interactive purpose. So I'll just go with the print. So this one will be node weight, or let me go with the dp include here again, dp include, or let me consider dp exclude, right? So this is fine. Now let me write the for loop here for I in range of n. Basically, this is fine. Let's make use of this thing, man. What do we call string interpolation here? Start with the f here. This is fine. Let me go with I 4D. So this is fine as well. So this one will be values of I. Values of I. This is fine. 6D. Or let me go with a one dp include or exclude. Dp include and exclude both we have to try, right? So I'll just go with the dp include of I. So let me go with a 10d here. This is fine. Or dp exclude here. Let me consider dp exclude of I here this time. Again 10d. Again 10d. Yep. So this is fine, man. Yeah, now let's make use of the print for the interactive purpose, right? So I'll just go with slash n. This is fine. Let me go with the maximum weight of independent independent set, right? Set on this particular tree or on this tree. So let me pass here this one answer variable. Mm, yeah, answer keyword. So this is fine, man. We are done with the code actually. So we have the idea on the algorithm. So whatever we have written, whatever the code that we have written. So this is the example usage from here. This is the example usage. Sorry, from here. This is the example usage, right? So now let's do one thing. Let me explain whatever the code that we have written, and then we can just run the code. Before running the code, we can just discuss the output, and then we can run the code, right? So now let's do one thing. So here I have considered values 311,546. So this is nothing but it's 3211. Yeah. So we went with 3211, not 31. So let me check this. Yeah, we can just go with 3211. This is fine. Uh, we are just assigning the weights to each node here. So adjacency, this one, whatever I have written in the line number 20 for I in the range n. So we are just creating the adjacency list for the tree, right? Then this one, whatever the loop that I have written. So here we are just the loop is adding the edges here, meaning we are building the connections between the nodes, right? Then we have made use of the keywords dp include and dp exclude, right? So this one, line number 26 and 27, dp include and dp exclude is nothing but these are the arrays to store the dp results for node, right? So then we are moving, then we have moved on with the this one, what do we call dfs helper method, right? So dfs of u comma parent nothing but this is the recursive dfs to compute the dp values bottom up, right? Bottom up approach. We are going with a bottom up DP approach, right? So we are going with a recursive DFS to compute the DP values bottom up, right? So then we are just going with the include sum and exclude sum here. So what does the include sum do here? Include sum, uh, it will start the include state with the node's own value. And what about the exclude sum? Exclude sum state, actually, we are starting the exclude state from the zero, right? So inside the loop, what we have done here, we are going with the DFS of v comma u in the line number 36, right? So we are just visiting the child nodes first, nothing but as I had stressed this one earlier, we are going with a recursive DFS, nothing but the post order recursive DFS, right? So we are visiting the child nodes first in the post order, right? So this is fine. Then we are going with the include sum equals include sum this one plus dp of exclude b. So this is nothing but if parent is included, then children must be excluded. If the parent is excluded, then we have to take the best child configuration. This one, line number 38, exclude sum equals exclude sum plus max of dp include of b, dp exclude of b, whatever we have written, right? So this is fine. After loop, so this one, what we are doing here, basically we are storing the values in the dp include of u and dp exclude of u. Finally, we are just printing the answer, max of this one, whatever I have written. So this one, basically max of dp include of root comma dp exclude of root, right? So this one I'm speaking of. Where did it go? This one, dp include of 0 and this one, whatever. So this is nothing but the root. We are starting from the 0, right? Instead of the root, we have passed 0. This is fine. So final answer is max of dp include of root and dp exclude of root, right? So this is fine, I believe. Next, what shall we do? So this is nothing but the example usage. Yep. Now, before running the code actually, so what is the output that we need to get here? First, we are displaying. So for I, this one, whatever I have written in the range and print I for D values, this one. So we are going with the node weight DP include and the DP exclude. So DP table actually we are displaying. This is fine. So maximum weight of the independent set on this particular tree, we have to get the output answer. Basically, the answer that we need to get here is 19 actually. Let's check the same. Just copy this one entirely. Let me come here, make your Python followed by the file name dot py. Yeah. So see, let me enlarge this one. Yeah, now you can clearly see here, node weight dp include and dp exclude. So node, we had 6 nodes, right? If you remember, right? 0 1 2, then we went for the left side. So for the 1 actually we went with the children 3 and 4. For the 2 we went with 5 and 6. Totally we had actually 7 nodes from 0 to 6. Yeah. So weight, I had shown you the example that we have considered, 3 2 1 1 5 4 6. Yeah. DP include, we are getting 19 2 1 1 followed by 5 4 6, which is absolutely correct. DP exclude, we are getting 16 6. 10 followed by 4 zeros, which is absolutely correct. So the output that we need to get here is bottom up. We are making use of the bottom up approach, right? So the last one. So here in this case, the first one, but bottom up approach we are considering. So this cell we have to consider. This cell we have to consider DP include. So the output that we got here is 19 actually. The maximum weight of the independent set of this particular tree is 19. We are not going with the top, this one, top down. So we are going with the bottom up. So the output will be present in the first cell here, this one, 19. Yeah. So the maximum weight of the independent set on this particular tree is 19. So we are getting the desired output. So basically, see, let me, I have already drew this one, I believe. So just give me a second here. Let me show this one to you correctly. So just consider here 1 second. So yeah, we are going with actually 0, 1, 2 actually 0, 1, 2, 3, 4. Here 5 and 6, 5 and 6, right? So here we have the value 3, for this 2, for this 1. Sorry, 1 second, 1 second. Uh, 1 second. The one we have 2, so this is fine. For the 2 we have 1, so this one will be 1. We have the value 5 here. This is also fine. We have 4 and 6. We have 4 and we have 6, right? So we have 4 and we have 6. This is fine, man. So this is the tree actually. See, the output that we need to get here is 19, right? So how we got the output 19 basically? So see, we have the leaves 3, 4, and this one, this part, leaf 3, 4, and 5, 6, the last one, right? The last level actually. If included, dp include is equivalent to the weight here. If excluded, dp exclude initially, it will be 0. For the node 1, we will be including 2 plus exclude of 3 plus exclude of 4, right? So this will be for the include, we get actually, I'll just write include. For the include, we get the value 2. For the exclude, so we will be going with a max of 1 comma 0 plus max of 5 comma 0. So this will be basically max of this one, 6 actually. We'll get the value 6, right? So this is for the node 1. So this is for the node 1, right? For the node 2, so again, the same thing. So we will go with include equals 1 plus exclude of 5 plus exclude of 6. So the value will be, for the value for the include will be 1. And for the exclude, we have to go with max of 4 comma 0 plus max of 6 comma 0, nothing but 10 actually, nothing but 10, right? So the output that we got here is 1 and 10 for the node 2. For the node 3, see here, we will be going with the same thing. 3 plus exclude of 1 plus exclude of 2. Nothing but here, this will lead to 3 plus 6 plus 9 accordingly with algo, right? So this will be 3 plus 6 plus 9. Sorry, 3 plus 6 plus 10, not the 9. Sorry. Yeah, we are going with the 3 plus exclude of 1 plus exclude of 2. Exclude of 1 is 6 and exclude of 2 is 10. So we have to get 19 here. So this is fine. And when we consider, so this is for the include. This is for the include. So for the exclude, we will be going with a max of include 1 comma exclude 1 plus max of include 2 comma exclude 2. Nothing but 6 plus 10. Nothing but for the exclude, it will be 6 plus 10. We will be going with 16. Yeah. So the final answer is this one, the include one. So this one, right? We are going with the bottom up, basically the last one, the first one actually that's present. Bottom up, if we considering bottom up literally, then it is the last one, right? So basically it is presented the first one actually within the include table. So this one actually in simple terms, right? Yeah, this one I'm pointing out within the output. Yeah, so the output that we got here is 19. The same thing, 19 we are getting here, right? So which is absolutely correct. We are getting the desired output as per the, so algorithm works absolutely correct here. Whatever the algo that we have written works absolutely correct. Yeah. Now this is it for the algo, man. It's simple, right? So this is it for the tree DP algorithm, also known as dynamic programming on the trees, right? So let's discuss the this one. Let me do one thing. Let me summarize whatever we have learned so far before moving on with the next algorithm. Yeah. So let's try to remember these 4 to 5 points. First point here is tree DP. First point here is tree DP uses recursion. 3DP uses recursion. So that is the reason we have imported as file, right? System file. And then we have set the recursion limit to 10 to the power of 6. Yeah. So 3DP uses the recursion and the DP states to it uses recursion as well as the DP states to solve the complex problems efficiently. And DP states uses recursion and DP states, right? So this is fine. This you have to remember. So the second point here is, so we will be making use of the post order DFS. As I had stressed this one multiple times, we will be making use of the post order DFS just to ensure the children are processed before parents. We have to process the children before the parents, right? Here in this case. So we will be making use of the post order DFS, basically which ensures or primarily which ensures children are processed before parents, right? So this is one of the things. Next, let's move on with the third step here. So this pattern is used in maximum weight independent set, right? Maximum. So this pattern is used for the maximum weight independent set. Weight independent set. So this is fine. This pattern is used for the maximum weight independent set. Yeah, this is fine. The next one is, so minimum. So we will be making use of this one in the minimum vertex cover as well, right? So we will be making use of it within the minimum vertex cover as well, right? So the final one here would be we will be going with the subtree sum and the diameter problems. Yeah, we will be going with the subtree sum and the diameter problems. And the diameter problems, right? So let me give your diameter problems. Yep. So yeah, now this pattern is used in, or the use cases are, this is used in the maximum weight independent set, minimum vertex cover, and the subtree sum and the diameter problems. Yeah, the final one here is the time complexity and the space complexity. So the time complexity would be big O of n for n nodes. Yeah, we can just consider big O of n for the n nodes, and this one, the space complexity is also big O of n because we are making use of the recursion, right? So due to the recursion and the DPRA and the depth of the recursion can go up to big O of n. We know this, right? The space complexity would lead to big O of n as well. Right. So this is fine. These are some of the very important points that I wanted to discuss with you guys. So next, actually, we are left with quite a few algorithms within the DP based algorithms, actually. Very few. We are left with 3 or 4 actually, max. So we are left with 3 actually. One is digit DP, another one is bitmask DP algorithm, and the final one will be DP on the DAG, nothing but the directed acyclic graphs, right? So these 3 algorithms we are left with: digit DP algorithm, bitmask DP algorithm, and finally the DP on the directed acyclic graphs algorithm. Yeah. So basically we are done with the this one. Today we are done with the tree DP. Next, we'll be discussing on the topic digit DP, right? So we are done with this particular algorithm. I hope the algorithm part is completely clear. For now, this is it. Thanks for watching, guys.